Right, we have 3 exam questions to work through. The first question is your absolute standard exam question. This involves Snell's law, refraction, and also critical angle. And we have to calculate various values and then draw or complete the path of the ray of light. So that's a really key thing that you need to do in the exam. So you might want to draw this out, just do a little sketch of this, and then try and figure out where this beam of light goes. Question 2 would be, I think, a grade A question. That's quite difficult. So this is a calculation that we alluded to in the previous video, where we're looking at the values of refractive index for an optical fibre and trying to choose the best one and why. And the final question, I would say, is a grade A star. There's no diagram given here, so you'd have to sketch out a diagram. I think this is really quite a challenging question. So give yourself a bit of time to answer these, pause the video, and then when you're ready for the answers, you can press play. Right, here we go, question 1. So, calculate the refractive index of the glass. So, that should be straightforward. We know that this first angle here is the angle of incidence, and the second angle is the angle of refraction. And we've got our Snell's law. And something that it doesn't tell us implicitly, but it doesn't tell us at all actually, we just have to assume that this is air. I think maybe in the exam question they'd tell you that it's passing from air, but if it doesn't mention another material, we assume that it's air. So the first material has got a refractive index of 1. So without that, we would probably struggle. So we're trying to find the refractive index of the glass, which is N2. So we can make N2 the subject, so divide both sides by sine theta 2. And we've said that N1 is 1, so we can get rid of that. So it's just going to be the ratio of the sines of the angle. So sine of theta 1, or sine of angle of incidence, 56, divided by sine theta 2, sine 30, sine of the refracted angle, and we should get 1.66. So your check here is always that if we can see that we have a deflection towards the normal, which we do, that means that the light is slowing down. So the value of n of the material must be greater than the value of the first material. Now that must be the case if we're going from air. It actually tells us it's air here. So if you've got a value of less than 1, then you've got it the wrong way around. You've made a mistake. So 1.66 sounds about right. Okay, part B is trying to find the critical angle. So let's have a look at this one here. So we've got our formula, sine of theta c is equal to N2 over N1. Now, possible confusion here is getting the ends the wrong way around. So it's a very understandable mistake would be to think that N1 is air and N2 is the second material, because that's what it was in part A. However, if we have a situation where total internal reflection is taking place, then these values are the other way around, and this causes lots of confusion. So if you imagine that it's going to take place over here, so this beam of light is going to reflect here, so we're going to find the critical angle at this point here, then the first value, N1, is 1.66. The second value is air, N2 is going to be 1. So that causes lots of confusion by getting the N values the wrong way around. So we need to remember that TIR takes place inside the material. So it's not going from air into the material, it's inside the material and trying to escape into air. So N1 is the refractive index of the glass, 1.66. N2 is the refractive index of air. So once we've got them the right way around, then we can find a value of 37. Sounds about right. We typically would expect it to be around about 40 degrees. Okay, so 2 marks for each of those. Let's have a look at part C. So this is a bit more difficult. 2 marks suggests it's relatively straightforward, but I think a lot of students get quite confused here. So you do need to understand some basic geometry about angles in a triangle and so on. So let's have a look. If we extended this line here, and we could draw a normal at this point, this is our reference point. So this would be 30 degrees, alternate angles, this would be 30 degrees. So the angle of incidence is 60 degrees. Now we need to compare that to the critical angle, which is 37 degrees. 60 degrees is definitely bigger than 37, which means that total internal reflection takes place at this point. Now, I think in the exam, a lot of students would make a mistake here and just think, oh, it's just going to refract out of the material, which is obviously incorrect. So we get reflection taking place, and we can extend the line down to here, and then we need to draw a second normal, because we don't know whether, or we need to work out whether total internal reflection takes place here. So once again, if this is 60 degrees, well, we have this corresponding angles here. This is 60 and this is 60. So we actually have an equilateral triangle here, 60, 60 and 60. So there's a little bit more geometry there. Oops, oh dear, everything's moving around. Go back there, thank you. So if this is 60, then 90 minus 60, the angle of incidence at this new point, this second normal, is 30 degrees. So here we know that 30 is less than the critical angle of 37, therefore TIR does not take place. So the beam of light continues on its journey and it leaves the material, and we know that it's now entering air, so it will speed up and bend away from the normal. So this needs to be greater than 30 degrees judged by eye. So you don't need to use a protractor here, but you do need to get approximately these values in the kind of judged by eye angles. So that's a really, really important thing that you'll need to consider, is completing ray diagrams inside some complex prism shape. Right, question 2. So this is a bit more difficult. I would say this is a grade A calculation. So the first part is relatively straightforward. We can calculate the values of the critical angle. So we know with our formula, sine of C is equal to N2 over N1. So we've got the core is 1.52. So that's our first value, because that's the beam of light is travelling through that to start with. So in both of these calculations, N1 is 1.52. And then we can do the calculation with N2 with these two values. So we can try that with 1.35. This is our first value. So there's quite a big difference between the values of refractive index in the first case. So we can calculate the value of critical angle, comes out as 62.6. If we do the calculation again with the second value of 1.42, the refractive index of the cladding, then we get a larger value. So let's just pause and think about this. We've said in the previous video that to reduce the problem of multipath or multimode dispersion, we need to increase the critical angle, and that's what we've done here. So our preference would be to use the second one, and we need to write something to that effect. So if we use the 1.42 as the value of the refractive index of the cladding, this is the better option. And our reason why is because, as we can see, it gives us a higher critical angle. And we might need to explain in words as to why that is. Because as we said previously, so this is our little sketch from the previous video. So remember that the colours here are just to illustrate the paths clearly. This would all be one colour of light. We're just showing different colours for clarity. So this illustrates the problem of multipath or multimode dispersion. And you might think, well, this is the problematic beam of light here, the one shown as the red arrow. So this is taking, because the angle of incidence is relatively low, then it's taking a much greater distance to travel all the way along the optical fibre. So what we're doing here is, with the second cladding value, by increasing the critical angle, then we might get rid of this entirely, because if the critical angle increases, then this beam of light here will no longer undergo TIR. It will just refract at this point here, and it will escape. So we'll lose that pulse of light, but that's what we want, because then if we can get rid of this in its entirety, let's just get rid of this. Can we delete these? Here we go. Then we're only going to have the pulses of light which have travelled a relatively short distance, so we get a reduced spreading out of the signal. Right, question 3. This is a really difficult question. I think especially if you're not given a diagram, you might get a diagram perhaps, or you might need to draw your own diagram. But the diagram is really quite crucial. So we've assumed that we've got the time taken for the light to travel the maximum distance and the minimum distance. So the minimum distance we're going to call x1, that's shown by the green arrow. That just travels all the way down the centre with no reflection whatsoever. So that would be the best or shortest route. The longest route is going to be where we get an angle of 60 degrees. So if the critical angle is 60, then just at that point we will get beams of light undergoing TIR. And we're going to call this path x2. And these are going to travel the furthest distance. So this is the maximum distance because there's lots of reflection all the way down, and we're trying to find out the difference between those two paths. So we need some kind of relationship between x1 and x2. So this is where a little diagram is quite useful, because if I imagine just over this short distance here, I've got a 90-degree right angle triangle, I've got the shortest distance x1, I've got the longer distance x2, so I can work out a relationship in terms of sine 60 between x1 and x2. So right angle triangle, sine of theta is the opposite over the hypotenuse. Opposite is x1, hypotenuse is x2. So this is the relationship between the values of x1 and x2, whatever those are. And you might be thinking, well, we don't know what the value of x1 is. Well, we don't, but this relationship is the same all the way along. So if x1 is 1 meter, then I can work out the relative value of x2. If x1 is 1 kilometre, I can work out the relative value of x2. So if you make x2 the subject, x2 is x1 divided by sine 60. x1 we're going to say is the total length of the fibre. The shortest route is 20 kilometres. If you divide that by sine 60, we get 23.09 kilometres. So I've worked out the difference in distances between the shortest distance, which we knew was 20k, and the longest distance, if we have a critical angle of 60, is 23.09. We need to use this value here, so be careful. Some students in the exam might have thought the speed of light is 3 times 10 to the 8. Well, it's slower, and we're told what it is. So I can then do a couple of calculations. V equals S over T, make T the subject, T equals S over V. So T1, for 20 kilometres, we can work out the time, that's 1 10 to the minus 4. T2, for our new value of 23.09, is going to be a greater value. It takes longer to travel this longer path, and we can work out the difference between the two. So it's just going to be the larger value, the second value, take away the initial value, and that is our answer. So we've shown mathematically why we need to reduce, or rather, why we need to increase the critical angle to reduce this time delay and the spreading out of the signal.